Today, I'm going to walk through a general model setup for a single lap shear test with two metallic coupons and adhesive, bonding those two together. You want to start in your part module and in your section sketch. Going to turn out these grid lines so the view is a little bit more clear. Effectively, you're going to want to start with modeling your specimen geometry, which is dictated by ASTM D1002. The lap shear specimen is recommended to be 177.8 millimeters long, which in this top-down view, you can see here along the length and base units, and 25.4 millimeters wide. This is shown here on this dimension, but it's divided by 2 because at the end of this model, we're going to mirror our results in order to best maximize the amount of nodes available in the Abacus Learning Edition. The thickness of the coupon is 1.62 millimeters, but because this is a shell element that is added later on and rendered in your thickness. Once you sketch and dimension your part, you can click done and you should generate a feature or something like this. The only other thing you're going to need to do in the part module is create a partition that represents where the two coupons will overlap. The way that I did this is by offsetting a point with this selection here. Sorry, one up from that, create a datum point offset from a point. You'll select that. You can select this endpoint here, dimension it 12.7 millimeters away, create a datum plane, and then partition with that datum plane using this little icon right here. And you should get something like this. Following that, your part is complete. You're going to duplicate your part. Here you can do copy and then just paste, and then you'll have the two coupons needed for this evaluation. The property module is where you'll set your material and your section assignments. Material tab is right here. Section creating is right here, and assigning your section is just under that. So these 3 icons are all you're going to use. Material is set here as aluminum. You want to do elastic behavior, isotropic. The Young's modulus and Poisson's ratio are shown here for a standard aluminum material. Once you have that, you'll assign your section to your entire coupon. So to do that, you'll select this. You'll go with a solid homogeneous section, continue, select the material you previously assigned. And right here is where you're under that thickness that I mentioned earlier. So for this coupon, that's 1.62 millimeters. And then you'll render that thickness later on to get the full view. I'm going to cancel out of this since I already have that set. But you'll basically assign that section that you just created like so. And you'll probably want to define it from the top surface, which basically brings your geometry down from what's highlighted in red. So it looks like one uniform thickness. Once you have your sections assigned, you can go to your part display options and render your shell thickness. My scale factor is set to 1, but this is where you'll get that thickness that you assigned to display as shown. Following this, you'll want to create your assembly in step. The assembly is pretty straightforward, but you're going to just want to have these 2 overlaps on top of each other, because your interaction that you care about is this surface right here where you have an adhesive. The suggestion is likely to offset these 2 instances and first do your interactions, because it'll be easier to select this surface when they're not in contact. And then once you set those interactions, you can go in and bring these 2 instances together just through translating the parts, which is fairly straightforward. So I'm going to skip through to, well, I'll go to step first. This is just where you create one static general step, continue, accept the defaults, click OK. I'm canceling out of that because I already have a step. But for interaction, this is where we're modeling the adhesive behavior. So you'll want to create an interaction between the top surface of this coupon and the bottom surface of this coupon. And that's represented here. You'll pick your surfaces, doesn't really matter how you pick them, as long as this is what you're getting at the end. You want to make sure your discretization method is node to surface. And you'll set your interaction property right here if you didn't already set it separately. I'll go into the interaction property to show you what you should have for modeling cohesive behavior. It's not quite as straightforward as other failure methods because adhesive can fail in a number of different ways, but you'll want to leave everything as the default here in cohesive behavior. Damage is a little trickier, but you're going to want to go through these 3 tabs. Initiation, criteria is quadratic traction as suggested by literature. You're going to want to use 29 here, which is the failure energy for a standard epoxy adhesive. Revolution, we're going to use type energy, specify maximum behavior through the BK method, and ensure you set the power law and exponent to 1.2, and your fracture energy is shown here. Really the only one that matters is the normal fracture energy. These you can kind of set to whatever. And stabilization, you'll want your viscosity coefficient at 0.0001. Once you have all that set and your interaction properties set, you are good to go with creating your boundary conditions and loads in your mesh. For boundary conditions, the left end is clamped down, so your U1 is 0. Your central axis is U2 and UR1 and UR3 set to 0 to ensure you don't get any strange effects from the mirroring that is going to happen later on, and because those don't move in that direction. And then your load is a displacement of 1.3 millimeters to the right, which is dictated by the standard, which effectively says that the machine will pull the right-hand sample at 1.3 millimeters per minute until rupture occurs. So once you have that set, you can go into your mesh. What's important here is to refine your mesh specifically at the overlap areas. So if you can see here, I have a pretty fine mesh here and a really loose coarse mesh going outwards. I'm trying to maximize the number of nodes I have available and concentrating all my elements here because that's where the interaction is that we care about. Everything over here is really loose. So you'll just do that through seating your edges and setting a bias as you move closer to that end. To query my mesh, you can see that I have 986 nodes, so pretty close to the upper limit, and 854 linear quadrilateral elements of type S4R, which is appropriate for this model. Once your job is meshed, you'll create this job and submit it, let it run. In the status, they'll show you whether it's complete or not. So while it does that, you can think about what you expect to see, which is likely stress concentrations between the 2 overlap surfaces. And that is shown by the model here. So if you look at your stress, you can see here is where your main response is, which is representative of what you would see with an adhesive holding these 2 ends together. The displacement is set at only 1.3 millimeters. So if you animate it, you'll see it kind of pull and stop. Theoretically, if you were going into a non-linear FEA, you could evaluate, and you'd like to evaluate this coupon being pulled far enough that it fails the adhesive between the 2 layers and the coupons are no longer attached. But because this is a linear finite element model, we're really just looking at the stress here to understand how the laminate or the metallic coupons are affected. And there's a lot of improvements that could be made on this model. You can see edge effects here due to what you would have the machine pulling on those ends. And like I said, you would want to model the adhesive failure, but this is a good starting point to begin to understand the adhesive behavior between 2 coupons in a lab shear test.